Okay, welcome everybody, and thank you for the invitation to this webinar. Let me start sharing my screen. Okay, I hope you can see my slides.
Yep.
All right, so as you will see, it's a relatively simple thing what I'm going to explain today. It's a simple classification of planetary atmospheres based on their most abundant abundances, so hydrogen, carbon, nitrogen, and oxygen only. And yeah, say good morning to you, or should I say good afternoon from Scotland. So this is the main paper I will talk about today, which just has been recently published. And here I want to thank my collaborators. So you see, this is a number of people from St. Andrews, not only in astronomy, but also from Earth Sciences. So we have also some of the co-authors are in the audience. So Oliver Herbert, Christiane Helling, Eva Stücken, Martin Dominik, Patrick Barth, and Dominic Samra. And I will also here a shout to Leonor Jansen, who recently extended this to Sulphur. So what's a biosignature? I think we are all want to detect them, right? I would say from my point of view, it needs to be some kind of unexpected combination of things we can observe for molecular features that are observable and which are not there in chemical equilibrium. This is the very point that I'm trying to make today. And then second, if we find such a deviation, then there must be a good reason to why this would be because of biological activity. These features should be in the near or mid-infrared, because the instruments are now looking there. We are probably probing something like a few millibar in the atmosphere. So this is the layers where we can hopefully detect something from. And the concentrations should be a few, maybe 100 ppm or 10 to minus 4. Otherwise, it's just very difficult to detect these features. So we are actually looking for rather abundant molecules. And therefore, the main molecules we will see are listed here. They're basically made of carbon, nitrogen, hydrogen, and oxygen. And the question is, can we find something already there in these abundant elements, certain fingerprint of life or fingerprint of some kind of biological activity? So that's why it says it's most pressing, because these are the things that we will observe. Well, one of the problems is that they should not be covered by clouds, and it's going to be more complicated. And another thought is that the parameters we can get from observation should be physically consistent with having liquid water on the surface. And so there's one paper who Christiansen Totten, who proposed in 2019 that we should look at a combination of methane and carbon dioxide without CO. And basically that was the start of the story. We thought, wait a minute, we have these combinations just everywhere in our models. So why do they say this might be a big biosignature? But before I move on, I want to spend about half of the time today to actually talk about the theory, to talk about chemical equilibrium, and to advertise my GGchem code before I move on and then talk about this particular paper, which is an application. So chemical equilibrium is part of the common LTE assumptions when it comes to determining the molecular composition of the gas. There are widespread applications in astronomy. For example, in brown dwarf atmospheres, or other cool stellar atmospheres, also in AGB star winds, and last but not least, in planetary atmospheres. Basically, there are two equivalent methods. Either you try to minimize the Gibbs-free energy of the system, or you solve Goldberg's law of mass action. This is identical if you have an ideal gas or a mixture of ideal gases. So this is written here. Yeah? So you see you have a molecule that is made of certain elements, ABC, and they have stoichiometric factors, small ABC. And then you can, in chemical equilibrium, the partial pressure of that molecule is related to the atom partial pressures. So not to be confused with elements, these are the partial pressures of the atom. They can be really, really small at low temperatures, but anyway, it's true in chemical equilibrium. And what you need to know is basically the Gibbs free energy, which is the one of the product minus the stoichiometric factors of the atoms. And then you can calculate the equilibrium constant. And then you can try to solve the system of equations, which is a high-dimensional nonlinear system of equations. And historically, there was a lot of papers, of course, about this. One train of historical models comes from stellar atmospheres, this is the lower one, and they usually solve Guldbach's law of mass action. There's also another strain of models that comes more or less from technical chemistry or theoretical chemistry, so not from astronomy, and they typically solve just minimize the Gibbs free energy. So what happens in my GGchem model, or our GGchem model, I should say, is you determine the molecular concentrations based on the total pressure, the temperature, and the element abundances. Now, how this is kind of to visualize what is going on. So you have a kind of cauldron here where you control pressure and temperature. Then you take, say, 1,000 spoons of hydrogen, 100 spoons of helium, and 10 spoons of carbon, and so on. And then you wait for eternity, and chemical equilibrium is established, and then you can read off what the molecular concentrations are. Now, for method one, so principally this equation, you have a high-dimensional system where the number of unknowns is the number of your molecules and atoms, and you try to minimize this. The method that I am following is following Guldbach's law of mass action, and there you can actually eliminate all the molecular partial pressures by the atomic partial pressures, and then the only variable that is left to determine are the atomic partial pressures. And then you solve a relatively low dimensional equation system, and the equations you're actually solving are the element conservation equations. Now, for small temperatures like 100 Kelvin or so, that there are some problems. The atomic partial pressures, so the actual variables we are trying to determine, are of the order of -10 to the power of minus several hundred. And the equilibrium constants are of the order of 10 to several thousand in some cases. So this is numerically actually quite challenging as you go down to low temperatures. In mathematical language, the conditional matrix, the conditional number of the Jacobian matrix of the system you want to solve becomes very, very large. But one can solve these problems all one by one. One trick I'm doing is I go to quadruple precision as it comes to low temperatures. That's a bit slower, but it's automatically done, if the temperatures are just low. And you have a system of very careful pre-iterations that is visualized here. So basically you do only the most abundant element, and then you add one element, and then you have the feedback between them into account, and so on. This is relatively fast, and then in the end you have the final complete calculation. And the code is carefully benchmarked against another similar code, which is called T from Blesic. So we did this in the 2018 paper. This is a benchmark where the task was, okay, we have 24 elements. We have no ions and cations because T couldn't handle charges. And then just take all the available molecules you have and come up with a solution. You start with 6,000 Kelvin and go as low as you can. And when you look at carefully here, so the full thick lines are the ones from GGchem, and the gray lines that are overplotted are the ones from T. And you see this is a perfect match. So this is really code validation. I've done several benchmarks in my scientific career, and this is the most successful I've ever seen. So this is quite amazing, actually, how good these two codes, although they are completely doing different things. One is in Python, one is in Fortran, one is using method 1, one is using method 2, but they agree completely on the results. However, that being said, GGchem is way much faster. So I'm using, it needs about 40 milliseconds per call 24 elements, whereas the T code under these conditions, which is quite difficult for the code at that time, used about 10 to 1,000 seconds. So that's a factor of almost 10 to 6 in speed difference. Now, another part of this equilibrium business is phase equilibrium. And with GGchem, you can also do phase equilibrium. Again, there are the two methods, minimizing the system gives free energy, or, and this is what we do in GGchem, computing the supersaturation ratios. And then for all condensates, you have this S, which is the supersaturation ratio. And we know in equilibrium, this can only be smaller than 1, then this condensate is not present, it's unstable, or it must be exactly 1. These are the condensates that are present, that are stable. And this means this is again a kind of numerical challenge because you don't know priori which are the condensates that I need to solve. So there are just a handful of equations you have now to also solve, but you don't know which ones. Okay, but again, the whole thing is only as good as your thermochemical data you put in. And the selection of the condensates is of course crucial. When, say you have a condensate which exists as a free molecule, then you can use this one. So this is the partial pressure divided by the vapor pressure, where the vapor pressure is some temperature function. But there are also cases for minerals where no such condensate, no such species exists as a free molecule. And then you can do this kind of generalized treatment where again, you are expressing everything as function of the atomic partial pressures. And here then the Gibbs free energy is then that of the condensate with respect to those of the free atoms. And this is how it looks like, you know, in this mode where you also solve phase equilibrium. So again, we have our element abundances. We take spoons of all that in the cauldron, control pressure and temperature. These are the initial or total element abundances. And then now, however, some of the stuff or lots of the stuff will actually fall out as a condensate. And so you need a kind of iteration. So we start by doing the chemistry here, then you get the molar partial pressures. From those, we can determine all the supersaturation ratios. Then we have to think about what could be under these conditions are the most stable condensates. So which of the supersaturations are largest? And then there's some switching on and switching off. And then you remove that condensate until you achieve phase equilibrium. You subtract those elements from the total ones. That gives you the gas element abundances. And then you can again solve the chemistry in the gas phase. And then you do an iteration. And here are some results from the 2018 paper. So this is the dust to gas ratio as a function of temperature here. And yeah, so you see that coming from high temperatures, for example, this element is the first one that condenses, and then comes zirconium and then aluminum. And so I marked in red always the elements that if they start to condense, then it makes an imprint really on the dust to gas ratio. And so around maybe 1,500 Kelvin at 1 bar, it's pressure dependent, but for 1 bar, it's around 1,500. You have formed all the important silicates and high temperature condensates, and then it becomes relatively constant for a while until only later you start also forming other things like phyllosilicates, for example. So these are silicates which have OH or water units in their lattice, so they can take in water and thereby actually increase the dust to gas ratio. And then finally, you also form the ices. So you form water, you form NH3 ice in this case as well. And then you end up with a value of about 0.01. In the lower diagram, you can see what happens to the elements in the gas phase. So the elements kind of disappear one by one. First, these high temperature condensates, and then later also something like sodium and potassium. But then, you know, these are the elements that are interesting now for planets because even at warmer temperatures, these are the elements that are remaining in the gas phase. They are not easily to be, not an easy way to condense. And so these are the elements that are left over. And this is what the planetary atmospheres are about. Now, this was from an talking astrochemist language. So we usually have we consider a numerous gas, mostly H2, and then also a little bit of dust is forming. When you talk to geologists, they have a very completely different view. So they rather look at the rocks, and this is what they have, and then the gas is relatively unimportant and forms like a byproduct of what's going on in geology. And this is a result here from my PhD student, Oliver Herbert, in 2020. So what we did here is studying the outgassing of common rock. So basically you have this very model, and you take continental crust abundances, so something that we can measure on Earth. And then you just lower the temperature from 5,000 Kelvin to 100 Kelvin, and here you plot what is abundant in the gas phase. And so at high temperatures, we have really a rock gas kind of, made of all complicated things like silicon monoxide, atomic things, maybe some hydroxides, metal oxides. And then, at some point, all the silicates form, and then you get a more, the gas phase is now more of the more less refractory elements. And if you think about that silicate, actually, the most abundant element is oxygen. So it's not surprising that if you can't condense all of them because you're still very high temperature, then a lot of oxygen is in the gas phase. So you get a very highly oxidizing atmosphere. As you go down, then you form iron oxide at some point. So you go from metallic iron to iron oxide, and that removes a lot of oxygen. Then you end up with a water atmosphere. Here you form phyllosilicates, forming a CO2 atmosphere, and further on, then there's also the condensation of carbonates, and then you're left with just nitrogen atmosphere. So this is a summary. So the GGchem code has already spread quite a bit until now. So you can freely download. This is a public code from GitHub. You can model up to 40 elements. Over 1,000 molecules are implemented from several data sources. The data sources are quite carefully checked against each other. We have about 250 condensates maximum. Most of them come from this JANAV. Oh no, but actually most of them come from this database, which is a geological database. And we have completed this by some of the NIST JANAV data. There's a customized selection of elements, molecules, and condensates. So you can also make a very fast, very small model where you have only a few elements, and then you can do whatever you like. It's an ultra-fast 490 code, so it uses about 40 milliseconds per call for 24 elements and scales like the number of elements to the power of 3. So if you have only a few elements, then it's much faster than this. It uses RealStar 8 arithmetics for high temperatures and RealStar 16 arithmetics for low temperatures. It's benchmarked. You can also switch on ions and free electrons. You can optionally include phase equilibrium, and you can choose either density and temperature or pressure and temperature as your thermodynamical variables. Okay, so now coming back to this particular paper where we discuss the low temperature composition of CHNO gases, or CHNO, the CHNO model. So these are now, look at the axis. So after some trial and error, we came up with these two axes. So on the x-axis, we have the carbon ratio. So this is the carbon divided by everything else, but not hydrogen. No, sorry, but not nitrogen, because nitrogen usually just forms N2, and it's kind of like an inert gas. So you can actually have this in addition to some nitrogen, and the results would still look very much the same. That's why I always subtract here just the N2. And then on the y-axis, we have the oxygen minus hydrogen, oops, sorry. divided by the sum of those. So this is a kind of axis where here, down here, you have highly reducing hydrogen-rich conditions, and up there you have highly oxidizing conditions. And for example, at this point, that would mean this is a pure H2O gas. Here you would have a pure CO2 gas. Here you have pure CH4. In the corner, you have pure O2. And in this corner, you have pure H2. And what's interesting is that there is this triangle, where things are just varying in a linear way, and then come these borders, and below these borders, all of a sudden the molecules are gone. So these white spaces is really, the concentrations are very, very low in chemical equilibrium. It stops here at 10 to minus 4, but it actually falls down even further, much further than this. There's only one example here where we have a little bit of a contamination, because H2 is something that is not that far away from the most stable configuration, and therefore a little bit of H2 shows up of the order of 10 to minus 4. But everything else, either you have it or you don't have it. And this can be seen again here. This is the same diagram with a cut. So x equals 0 is here on the left, and x equals 500 is on the right. And here I'm plotting these logarithmic concentrations, and you see there are these particular artifacts, particular points where one molecule completely disappears and it is exchanged by another one. So in this region, which we call type B, there are only these 4 molecules and nothing else, more or less, down to 10 to minus 6. There's nothing else. Then O2 disappears and we get CH4 instead, and nothing really happens. Actually, when you would plot this in a linear way, this would be straight lines. So the dependencies here are linear until you're losing the CO2 and then form NH3 instead. So that's why you have this distinct region, which is where things are quite similar chemically, but then very different from, say, type B or type A. Type B is oxygen rich, type A is hydrogen rich, and type C is something that I would call the default. And I would explain that later why I think this is the default. There's also this region, which is kind of forbidden by graphite condensation. So here you would have even more carbon than CH4. So take CH4 and add a little bit of carbon, then that carbon just doesn't know where to go to, and you would get direct carbon condensation. And so this is always here forbidden by condensation. And now let us ask, or let us examine the question, why only 4 abundant molecules at a time? Why is that so? So let's take one example reaction between molecules A, B, C, and D. We have 2 reactants and 2 products. Law of mass action would be this. So you have the combination of products divided by the stoichiometric combination here of the reactants. And this is given by exponential minus delta G over RT. And now, so this is the reaction Gibbs free energy. And for low temperatures, you can forget about this term here. Basically, because the temperature goes to 0, you only are left with the reaction enthalpy. And that is also quite constant as you go down to lower temperatures. And so when a reaction is exothermal, it means that the reaction enthalpy is smaller than 0. So you get a negative thing here divided by T. So for very low temperatures, this means it's plus infinity. So the whole thing is huge. And that means you have no A and B. On the opposite side, if you have an endothermal reaction, then the reaction enthalpies are positive. And then you get the opposite. You get only C and D, but there's no, you have no C and D, but only A and B. So you can say that for low temperatures, the law of mass action becomes something like a binary operator. It says just yes or no. So then the only thing that you are left to solve is the element conservation, knowing that all the other molecules are actually not relevant. And there's a little game you can play. So this is actually great. Although I never did this in COVID times, I wanted to do this always with a bunch of students. So imagine you have just a given number of oxygen atoms, hydrogen atoms, carbon atoms, and nitrogen atoms. So 8 over 26, 26 is the total number of bullets here. And now we know that basically we want to minimize the Gibbs free energy. And the formation enthalpy is the only thing that matters because this term is not there. And this is, unless a minus sign, is the so-called atomization energy. So you can say, this is the energy that I need, for example, to take CO apart. This is the energy I need to completely take apart CH4 into atoms and so on. So given this table that comes from Nistyanov, what is now actually the solution? So just imagine instead of electron volts, you say dollar, and then you want to maximize your profit. Yeah? So you have all the bankers are on board immediately, and then you give them time to think about what is the actual solution. And when you do this, yeah, when you go to Casa and you want now to have your dollars, then the best is $115. And the solution is 2 water, 3 CO2, 1 CH4, and 3 N2. And you can do this by actually stepwise eliminating all the molecules. At some point, you will find that there is a particular set of molecules. This is water, carbon dioxide, methane, and N2, by which, if you have any other molecules, you can react with one of them by an exothermal reaction and form only other members of those 4. And that would be actually my definition of a good non-equilibrium marker. Because when you have any of those molecules, so this is my equilibrium soup sketch, for example, NO, you can form an exothermal reaction with CH4 that creates only these 4, and so on. So all these molecules, all the alien molecules can be converted in an exothermal way to finally only form these 4. And that's why I say this is the most favorable set of molecules, the kind of mother molecules. You will only get these 4 if your element abundances allow. That maximizes your profit. However, if the element abundances do not allow that, for example, you have a huge amount of O2, then you form O2 in the end. If you have something left over for hydrogen, then you form H2. And this is then related to this type B and type A. Okay, coming back to the results. So this is the result for 200 Kelvin, 1 bar, and low nitrogen. And there was a little dispute with the referee. So we said, basically, it's always the same. It's very robust against changes of temperature and pressure, but the referee demanded to see that. So you see in the paper, there's an appendix, where you have 5 almost identical figures. So this is variation of temperature, low temperature, high temperature. Here you see again a little bit of contamination with not so stable molecules. This is because now this term kicks in at about 600 Kelvin. This becomes important for a few of those molecules, for H2 and for CO. So there's a little bit of contamination there. Otherwise, it's really identical. Yeah, if you look at the other plots, there's no difference. This is variation of pressure, looks the same. High pressure looks the same. Variation of nitrogen abundance, this is now very high nitrogen. And you will see a small difference here in this area because there's actually, there's the subtraction of N2 doesn't really work so well. But it's a minor thing in my view. So how to go from here? We recently had a finished final year project by Leonie Janssen, who was also in the audience. And she expanded this idea now to have not only CHNO, but also have CHNOs, including sulfur, because this is the next important element. And this is what she found. So basically, from the 3 basic types, there are now additional subtypes. And this is the table, where you see that things are getting more complicated. In this case, you always have 5 molecules, and there are just a few more combinations possible. But you need, in order to make that relevant, you need maybe sulfur abundance of the order of 1%, which is normally not what we see in the solar system. In the atmosphere, the sulfur abundance is quite low. So the extent of this interesting regions are kind of linear with the sulfur abundance. So as you go to 1%, then it looks already quite close to here. So everything comes closer together. And in the end, you find again the basic types ABC. But for example, B2, this is quite interesting. If you have only 1% of sulfur, at some point you would lose the water, and instead you would form SO3 as a stable molecule. And when you look at the sulfur abundances in the solar system, so that then one should actually look at this with a third axis. So these are now the same axis as before. So this is oxygen, hydrogen, or reducing, oxidizing conditions with the total carbon. And now you have something like the sulfur abundance as well. And then you can plot actually the different objects we find in the solar system. Earth has very low, of the order 10 to minus 7, maybe because of life, but basically of human activity, of burning bad coal, of having this in the air, blasted in the air by coal burning. Jupiter is already a bit higher than Venus, the order of 10 to minus 4. But then there's also strange objects like Io, which is basically pure SO2. There's not really an atmosphere, but the little stuff that is there is mostly SO2, so that would be high up here on this graph. Okay, now an important thing is what actually happens with condensation. And in this diagram, if you think about you are now condensing graphite, then you would actually move to the left, right? So nothing changes here. When you remove carbon, you only make this smaller. So you go from the right to the left, but you will not go into this region B or not go into the A because graphite is not stable there. If you consider the same for water, here we have pure water. If you remove the water, your point will move in this diagram. It will lose both hydrogen and oxygen. And because it's all linear, this is kind of long straight lines here. So, and this point is when you have pure H2O. When you start here, for example, you have a little bit excess of oxygen. And then if you remove water, you are left with some oxygen. So all the points above this line will go up as well. All points below this will go down. And this is now interesting to discuss maybe potential evolutionary effects. So let's have a look again at the supersaturation ratios, how that looks like. Unfortunately, this depends now actually on nitrogen. So therefore we have two figures. But in each figure, we have the same axis. And now you see supersaturation ratios equal to 1 graphs. For example, this line here would be the points where the supersaturation of carbon equals 1 at temperature of 500 Kelvin. As we lower the temperature, that line takes more and more space of this inner triangle here, of this type C. And it seems that you have now completely forbidden in the end, yeah, this region maybe here, but there is water condensation. So on the other hand side, you have water becoming stable at around 350 Kelvin on the left here. And so the line is here, and inside you have supersaturation. So this is not a stable configuration. That gas would form some kind of water clouds, and that would move towards the edges of this shaded region. And then as you lower the temperature, you have to move more and more until in the end, there's almost no white spaces left where you can actually have a stable atmosphere for long times. That depends a little bit on nitrogen because, in the end, when you have more nitrogen, you have smaller partial pressures of the other molecules, and that means you have less condensation. So here, for example, you still have some white spaces where you can have a stable planet, in principle. Here you can have stable planets here, but only if the temperature is not too low. Yeah? If it's too low, then you're really dragged somewhere either into this region or into this region for say, temperatures like 300 Kelvin, then you have to end up somewhere here and there. And there you see the planets. So Mars and Venus is almost pure CO2 atmospheres. They are just situated at the borderline between phase A, type B and C. Earth is sitting right there where it should, because the supersaturation at the equals 1 line for 300 Kelvin. So we're having the water content we do because we are just having saturated water. And then there's also Jupiter here, which is pure hydrogen. We have the Archean Earth as another point here, interestingly. And Titan is pure CH4. And now the question is, when I start now with something, I put my initial model there, and I say I want to cool it down. How would that actually look like? And this has been also discussed in the paper. So here you see a number of models that are moving around in this plot because of condensation. So there are 5 models, these ones, where you have quite complex models. These are 18 elements models by Oliver Herbert. We have recomputed that for 1 bar here for this paper. And for each model, the model starts at the circle. For example, this one, yeah? Here we would start at the circle. Then there's a cross, meaning that instantly we start graphite condensation. And as we are now lowering the temperature, the thing goes to the left as we expected. And since it's situated above this line here, at the point where water starts to condense as well, we are now having both. We are having graphite condensation and water condensation. And there you see this development that actually finally goes very close to this boundary and makes a Mars. This model, very similar initial condition, but this would go and make the Titan. Whereas this model, it needs to go to the left because of carbon condensation, but then it doesn't know where to go to because it's exactly the stoichiometric ratio of water, so it doesn't move here from this axis, but ends up actually somewhere here. These are the simple models, so these are easy to understand because they are only having these 4 elements, H, C, N, and O. But there are these other models, they are a little bit more complicated. And this is because now you have 18 elements and there are lots of condensates and they are having different effects on how the element abundances change. But still the outcome of this outgassing of that rock is mostly contained by these 4, is mostly having these 4 elements only. So it still makes sense to make a point of these models in this graph, because these are still the major elements in the gas. So for example, this model here is very interesting. This is a MORB model, so mid-oceanic rich basalt as initial element, and we start here, then at some point we move because of water condensation. No, I shouldn't say that. I actually don't know. Which the condensation that takes place is very complicated. At some point, it hits the graphite condensation point, and then it actually turns around and makes it back to this, and finally results in a Titan for very low temperatures. But for example, this model, which is here, which is continental crust, that would actually move on just at the boundary between the 2 types and reaching a state close to Mars or Venus in the end. And so, by the way, these developments are never changing type. So you never cross a boundary by condensation. We never saw that in the models. It seems that whatever you do, these A, B, C type are still kind of maintained, even if you have very complex condensation. But for example, this model, which is CI chondrites, it's very complex. Yeah, you have all kinds of phyllosilicates are forming and carbonates are forming. So it goes to the boundary, but then it evolves along the boundary towards Titan at 200 Kelvin. If you would go even below, then things might get a little bit more complicated, because then you would also expect CO2, CH4, and NH3 ices to condensate, which is not considered here. I mean, we have it in the model, but we stopped the model there. It's complex enough. All right, so that brings us to my conclusion for today. So I hope I could explain to you that these four molecules are special. So water, carbon dioxide, methane, and N2 are the thermodynamically most favorable molecules in the CNO system at low temperatures. And in chemical equilibrium, we find basically three types of atmospheres, say between 200 and 600 Kelvin, which is relevant for the rocky exoplanets, for example. Type A is hydrogen-rich. It has water, CH4, NH3, and a combination of N2 or, no, it has not a combination, either N2 or H2. Type B is oxygen-rich. It will have O2 and water, CO2, N2, like in the Earth. Type C would be a combination that is not seen in the solar system. However, this is a kind of natural thing because, you know, you would say these are the most stable molecules there are, but it's affected by graphite condensation. So a lot of the space that is in this area, in the central triangle, is actually kind of forbidden by graphite. But if you would have some warmer exoplanet temperatures, warmer exoplanets, say above 400 Kelvin, then they could actually sit right there. That would be a completely new type of atmosphere. Second point, or third point, the classification by this oxygen-hydrogen ratio and the total carbon seems to be very interesting because it's very robust against any changes of temperature and pressure. This seems far more useful than the usually used carbon to oxygen ratio and metallicity. In particular, all kind of cloud condensation or condensations in general seems not to be able to change this atmospheric type. When you look at solar system observations, and I mean, maybe I'm leaning a little bit too far out of the window, and maybe some will say I shouldn't say that, but I would say the abundant molecules, the molecules we see that have percent abundances are actually in chemical equilibrium. This in the end is just a thing of stoichiometric ratio and element abundances. They have to go somewhere, and these abundant molecules are always going where they should, according to this model. For example, take the Earth. Most of it is nitrogen, so you form N2, fine. Next comes oxygen. The model says you form O2. You don't form any nitrogen-oxygen compounds, you form O2. This is what happens. Hydrogen should form water. This is what it does. Most of the hydrogen by far is contained in water, and so on. Also, carbon goes in CO2 and not CO. So in that sense, the very abundant molecules seem to be well described in chemical equilibrium. If we're looking for non-equilibrium effects, we have to look actually at the ppm or ppb molecules, because the non-equilibrium will be imprinted there. And one more remark, two more remarks about these non-equilibrium markers, right? So this is a first step towards a biomarker. It should be something that is not automatically produced in chemical equilibrium. And I would define a non-equilibrium marker as a combination of, first, a molecule that reacts exothermically with one of these three. And this combination of that molecule and the reaction partner, if we detect this simultaneously, then we know something is particular, something is remarkable. So that would be a good starting point for finding biosignatures. And then in the end, you know, this is of course not a biomarker yet. Then we have to talk to biologists, etc. What could be the cause of such deviations? But the one that has been proposed, namely the combination of CH4 and CO2, this works actually well in type A and type B atmospheres, but it doesn't work obviously in type C, because these are abundant molecules anyway. So they have similar abundances according to chemical equilibrium. And this is, if type C atmospheres exist, then this is likely to just produce a lot of false positive detections. Okay, this was my talk, and thank you very much.
Thanks, Peter. So we will open it up for some questions. Please use the raise hand function, which is on the bottom. If you go to reactions, you can see a raise hand, and then I'll go ahead and call you. I see you already have a question. So it's Eric, go ahead, take it away.
Hi, Peter. Fantastically interesting talk. I was a little bit confused by the points you were making that type C atmospheres are not stable in the solar system because of graphite condensation. But then you said that condensation doesn't cause objects to change between types. So what happens to a type C atmosphere when you drop it below 400 Kelvin?
Yeah, so first of all, it depends a little bit on nitrogen ratio. This is what I tried to explain here. But at 400 Kelvin, let's take this thing here. At 400 Kelvin, you would still be able. This is 400 Kelvin, so this is like this graph. Yeah? So there are still some white islands. So at 400 Kelvin, they should just be there without. At this point, they could rest without any further condensation. As you go deeper in temperature, then the water comes and drives the system up. And this is, what you can see this with the dots here. So all these models will then be almost exactly at the boundary between the two types, because the condensation enforces a path like that. But it will never leave it. Yeah. So you're getting very close to this theoretical boundary, but you never cross it. But in the end, as you go to deeper and deeper temperatures, you would, so if point here, you would expect this to be somewhere there, depending on how low you go in temperature. However, in real life, it's a bit more complicated because there might be some other condensates which are not covered by these simple models, and then you can actually make the way to the other end.
I see. So you basically either collapse to a Mars-like atmosphere or a Titan-like atmosphere.
Yes, indeed. Whereas here you go up, basically, and then you make an Earth.
See, any more questions? I actually have a question for you, Peter. So on the CO2 and methane, a potential false positive for the biosignature. So if those are, you mentioned that's maybe more of an issue for those warmer temperatures. So if you are trying to use that as a biosignature, if you can constrain temperature, have you kind of, avoided that potential false positive if you can look for something at 300 Kelvin? And
absolutely. I think you're perfect, spot on, right? Yeah. So this we don't really know whether it's type C or type B in the mathematical sense, but it's a kind of strange question because we have abundances that are very, very close here on that line. The point that I wanted to make is just that, we know that the CH4 is a very good biomarker on the Earth. But what I want to say is that if there are type C atmospheres around, and there could be when they are just slightly warmer, like 400 Kelvin, 500 Kelvin, if you have a rocky planet with such conditions, it is very natural to assume that some of them might have this and could lead to a false positive detection. But if we know for sure that the temperature is quite low, then I think then it's not an issue, right? So we could combine this with a robust knowledge that this is a very cold case, and then you shouldn't have CH4 because graphite condensation. Yeah.
Gotcha. Let's see. Before I have another question, but I'll wait a couple of seconds to see if we get any other hands. Looks like we don't have anything yet. So I've used GGchem and I think it's very easy to use and it's really nice to be able to set those up. So in terms of, have you worked on adding photochemistry, thought about that? I know it's a monster. I know it's a whole separate thing to add on, but it's, this code is so quick and it, can iterate so quickly. It seems like it's possible.
No, that is really, as you say, it's a very different beast. There are many codes around which do kinetic chemistry, and that's of course, compared to what I have explained today, this is the real world. Yeah? So I know that this is a kind of tool that is nice to have, and for some, say relatively high densities pressures, if you're discussing, say, the bottom of the atmosphere, that it might be very useful. But in the end, photochemistry is, of course, will change things, and you need a kinetic treatment of that if you want to do this properly. The whole setup of the code is not made for that. Yeah? So we are not solving a kinetical rate network. Other people do this much better.
Gotcha. Yeah, totally understand. So I think Sanjay, you have your hand up. Feel free to go ahead and ask a question. I think you might be muted, Sanjay.
I still don't hear anything.
Yeah, I'm gonna see if you can. Maybe it's just
okay. Can you hear me?
Yeah,
we can hear you.
Oh, okay. Yeah, very interesting talk. I just had a sort of a question or a comment, I guess. Your analysis applies to a global situation, or is there a possibility of local disequilibria conditions?
okay, so the code and what I showed, the applications is just always one point. But of course, you can feel free to use this as a tool to, for example, have a structure. So this is actually something we have already done a lot of times. And Oliver Herbert is about to publish a paper about cloud stability, where you have a structure, a one-dimensional structure. You could also use a three-dimensional thing. Yeah? If you want to just to solve your equilibrium, you just call this point by point, and then you can construct a three-dimensional structure. Because in the end, if you believe in chemical equilibrium, there's no history, there's no connection to other points, right? It's only that point. Only the temperature and pressure and element abundances of that point are matter for the solution. So in the code, when you download it, there's a simple examples how to make one 0D model, so 1 point model, how you make a structure, or how to make a phase diagram where you vary temperature and pressure in a more a systematic way. But in principle, it's easy to do. Yeah? With the code, you just add a subroutine where you do your thing you want to do.
Thanks. In the case of Venus, we have a situation where the CO abundance is variable with latitude and with altitude. And of course, other gases, we're not sure what they do, like methane.
Okay, yeah, because you're mentioning Venus, so there's a recent paper out by Paul Rimmer, where I'm also a co-author, and where GGchem was used to approach the problem, what happens at the bottom of the atmosphere. And our conclusion is that, at the bottom of the Venus atmosphere, conditions seem to be actually fitting quite well with equilibrium. So we have phase equilibrium with the crust, and also equilibrium in the gas phase. So the concentrations there seem to be in accordance with the results from GGchem. If you just run it for the kind of observed element abundances of the crust.
This is a different paper than the one that I'm aware of in arXiv about the sulfur dioxide.
Yeah, no, I think it's the same there. It contains, it contains a lot of things. So there's a kinetic model from Paul, but there's also a little bit about the foot point of the atmosphere, which I contributed to this paper.
Oh, very good. I'll like to read that carefully again, because I think the one.
This is where also the pH value of the droplets is discussed. And so.
Right, yes. Yeah, that's what I was focused on. But the other question that has been nagging a few of us is, if you look at the water vapor profile, it seems to increase from the surface to about 40 kilometers. And what explains that?
Yeah,
why?
I mean, there's a lot of open questions. Yeah, we see that it's, as you go up in the Venus atmosphere, for example, in equilibrium, you would lose the CO, but you don't. Yeah, what I get with GGchem at the bottom is okay with the CO, with a measured in situ measured concentration of CO, but as you go up, you go to lower temperatures, and there, according to equilibrium, you lose it. Whereas Paul explained to me, CO is actually produced at the top via photo process and then diffusing downward, and that's why you get also CO in the kind of between the clouds and the surface. That you also get almost constant CO there. I mean, be aware this is a very simple equilibrium solver. So don't expect miracles from it. So, but things can be used sometimes as a ingredient of as an ingredient of more complex models.
Yeah, I mean the question is, where is the source of water, and why does it increase with altitude to the base? But that's for future exploration. Thank you.
So any more questions? So I'll wait another couple seconds. If not, I also endorse the idea that there are a lot of open questions on Venus that are interesting. But I think we should all thank Peter again for an excellent talk. And if you have questions for him, Peter, I can just forward on any of them to your email address. Sorry.
Yes, please. That would be fantastic. So I'm happy to take more questions if there are any. Or if you want to use GGchem for your own research, you can always just try to download and use it. But if you have a question and something is not working, feel free to contact me.
Okay, awesome. Thanks, Peter. Thanks everyone else for attending as well.
Yep. Bye-bye.
Bye, everyone.